Commander, let's light the sky. Training sharper drone pilots, learning how to fly. Mission ready mindset, safety leading every plan. Skills that build confidence from takeoff through the scan. Tune in at Sky Commander, come join the crew today. Learning smart, fly with purpose, level up your way. We see more, no sooner, that's the edge we're here to spread. See above, go beyond, get ahead.
Okay, let's get started.
So, imagine you're building this massive, I don't know, let's say a $2 million bridge extension.
Okay, high stakes.
Right, very high stakes. And you're basing all your engineering on this spatial data that just look absolutely flawless on your computer screen.
Which it always does, right? It looks beautiful.
Exactly. But then, months later, the construction crew is out there, they're pouring concrete, and you suddenly realize that the digital ground you designed this entire project around, it wasn't actually the ground at all.
Oh no, it was the canopy.
Yes. It was this optical illusion. It was just dense, low-hanging tree branches that your software, essentially smooths over to look like a solid dirt hill.
And by that point, you were in so much trouble.
Oh, you were looking at catastrophic delays, massive financial liability, and just a deeply, deeply uncomfortable conversation with the client.
That's the nightmare scenario. And frankly, it happens way more often than people want to admit in the architecture and engineering world.
Well, and that is exactly why we are doing this deep dive today.
Yeah.
We are tearing apart the illusions of 3D reality capture. Because, you hire a drone operator, they fly your site, and a few days later, you get this massive 3D file.
And it looks incredible when you open it, like a high-end video game environment.
Totally. It feels like they've just magically captured reality, put it in a digital box, and handed it to you.
Right, but then you actually try to use it.
Exactly. You try to integrate it into your workflow, and suddenly your workstation just absolutely crashes because the file is so heavy.
Or it loads, but the coordinates are completely out of whack. Like it doesn't align with your CAD drawings at all.
Yeah, and you zoom in on what you thought was this perfectly sharp building edge, and you realize, wait, I can't actually tell what's a wall, what's a tree branch, and what's just random digital noise floating in the sky.
You have officially entered the diagnostic muddy waters.
Which is such a good way to put it. So our mission for this deep dive is to unpack exactly how professionals take that raw, chaotic spatial data and transform it into trustworthy, actionable evidence.
Because a point cloud, and this is so important, it is not valuable just because it takes up 50 gigabytes on your hard drive.
Right.
The real test of an operator isn't when the drone lands safely. The real test is when you, the end user, open that file and try to extract a measurement that you are literally betting your professional license on.
I love that, betting your license on it.
Yeah.
Because true professionals in this space, they aren't just handing you data, they are systematically reducing uncertainty.
They're not giving you homework, basically.
Exactly. But before we get into the mechanics of how they do that, I feel like we need to address the psychology of the person looking at the screen. We have to shatter this central illusion of the point cloud.
We really do. Because the untrained eye, when you look at a dense point cloud, your brain just instinctively perceives a solid 3D model. Our brains are, they're incredibly efficient at pattern recognition.
They want to see a solid object.
Right. But a point cloud is not a watertight solid. It's not a continuous surface. And it is certainly not a mesh by default.
So what is it exactly?
It's simply a massive, massive collection of irregularly spaced, discrete measured samples that are just floating in a 3D coordinate system.
Like billions of individual dots.
Exactly. Billions of isolated spatial observations.
The LiDAR sensor doesn't hand you a complete building. It hands you a bunch of independent points.
I was actually looking at the anatomy of just one of those points. Like if you strip away all the pretty visual rendering, it's basically just a line of data.
Yeah, just text, basically.
Right. So you have your X, Y, and Z coordinates, which establishes exactly where that point is in space.
Yeah.
Then you have this intensity value, which tells you how aggressively the laser pulse bounced back off whatever material it hit.
Which is a hugely misunderstood metric, by the way, but we'll get to that.
Yeah, we definitely need to circle back to intensity. And then you also have a return number, which I found this fascinating.
The return number is critical because from what I read, If a laser pulse hits the very top of a forest canopy, it can actually break apart, right? Like part of the laser hits a leaf, part of it keeps going, hits a lower branch, and then maybe a tiny fraction of it finally hits the dirt.
Exactly. The sensor records that entire sequence. First return, second return, third return, all the way down to the last return, which is usually the bare earth.
And then ideally, you also have a classification code tagging that specific point as ground or vegetation or a building.
If the operator did their job right, yes.
Right. So I was trying to visualize this earlier, and I have an analogy. Let me know if this tracks with how you see it.
Okay, let's hear it.
So to really grasp how fragile this data is, imagine you're standing in the middle of a massive, completely pitch black football stadium, like zero visual information.
Just total darkness.
Total darkness. Now imagine you have this machine that just starts firing billions of tiny, sticky, glowing beads in every possible direction.
Okay, I'm with you.
And as those glowing beads hit the concrete bleachers and the steel railings and the field, they stick to the surfaces and they light up.
Oh, that's good.
Right. So very quickly, the shape of the stadium starts to emerge out of the dark. But the catch is, you don't actually have solid concrete walls.
You just have a spatial hint system.
Exactly. A hint system made of glowing dots.
Honestly, that is the perfect mental model. Because if you're standing 50 yards away in that dark stadium and enough of those glowing beads stick to a wall, your brain connects the dots.
You just see a wall.
You see a wall. Your brain is doing all the heavy lifting of interpolation. And, the commercial viewing software is designed to help that illusion along by shading the points to fake lighting and shadows.
But underneath, it's totally porous.
Completely porous.
So let me push back on this a little bit, because I know there's a project manager listening right now who's thinking, okay, but if I open the file and my brain sees a utility pole and the software shades it so it looks exactly like a utility pole, why does it actually matter that it's technically a porous collection of dots?
Right. If it looks good, who cares?
Exactly. If the visual illusion lets me understand the scene, isn't that good enough to get the job done?
And my answer is, it is absolutely sufficient if your only goal is passive visualization. Like, if you're just taking your client on a cool digital tour of the site.
Just flying around the 3D model.
Yeah, just sightseeing. But it becomes a literal disaster the second you need to extract an analytical conclusion from that data.
Because of what, exactly?
Because of occlusion.
Okay, break that down.
Occlusion is essentially a data shadow. It's not a shadow cast by light. It's a shadow cast by physical geometry blocking the sensor's line of sight.
So, something blocking the glowing beads from hitting the surface.
Exactly. Think about a building that has a really large roof overhang. From a drone's aerial perspective, the sensor captures the top of that roof perfectly, but the wall directly underneath that overhang, it's completely occluded. It is in a data shadow.
The beads never hit it.
Right. But when you look at the site from a wide top-down angle, your brain sees the roof, it sees the ground around the building, and it subconsciously just assumes that connecting wall is there.
Visually, it feels totally complete.
Right. But if you try to measure the distance from the edge of that roof down to the wall,
you literally can't.
You can't. The wall does not exist in the data set. Or, going back to your intro example, think about a dense tree canopy over a drainage ditch.
Oh, man. Yeah.
From above, that canopy looks solid. You might even assume the ground just follows a nice flat trajectory underneath it. But the actual laser sampling of the dirt beneath those leaves might be practically non-existent.
So if you run some kind of automated volume calculation or a water flow simulation, you are building these highly confident engineering conclusions on top of massive data voids. You're trusting the picture of the cloud instead of the structural integrity of the cloud.
Perfectly said.
Which I think perfectly sets up this massive disconnect we see between amateur drone pilots and actual professional spatial engineers. Because if a point cloud is just billions of potentially occluded hints, simply handing those raw hints over to a client is the fastest way to destroy any trust you've built.
Oh, you're not just handing over data at that point. You are handing over liability.
And the amateur operator often doesn't even realize they're doing it.
They really don't. They suffer from this fundamental misunderstanding of what their actual deliverable is. They think the value is in the acquisition. Like, I flew the drone, I navigated the airspace, I downloaded the file. The hard part is done.
Here's your 50 gigabytes, invoices attached.
Exactly. But delivering an unprocessed data set directly to a stakeholder doesn't deliver value. It just delivers extreme friction. And if you audit enough of these handoffs, you start to see the same 5 quiet killers of credibility over and over again.
I really want to spend some time on these 5 killers because I guarantee anyone who receives this kind of data has experienced the pain of at least one of these.
Oh, absolutely.
Let's start with the first one, which is just classic. The giant raw dump.
Yes.
This is where the client just gets an email with a Dropbox link to an 80 gigabyte file. There's no re-80me document, there's no metadata, there's no explanation of the coordinate system, just a massive monolithic block of data.
And the irony here is that the amateur operator usually does this under the guise of transparency.
Like they're doing you a favor.
Right. They genuinely believe that by giving you every single byte of raw data the sensor collected, they are providing maximum value. But an unstructured data dump is practically useless.
It's just overwhelming.
Completely. If you look at the strict deliverable requirements from federal bodies like the USGS, for example, a professional data set is essentially a highly curated library. It requires statistical reports, coverage maps, trajectory logs, explicit coordinate declarations.
Because when you just dump a raw file, the client might spend 3 hours just trying to figure out which software program can even open it without crashing their machine.
Exactly.
It's like imagine hiring a contractor to build you a house and they just drop a massive pile of unmarked lumber and a bucket of nails on your driveway, throw away the blueprints, and expect you to be thrilled that they delivered all the materials.
That is exactly what it feels like.
You don't have a house. You have a massive problem blocking your driveway.
Right. Which brings us to the second credibility killer, skipping cleanup.
Ooh, this one is rough. This is the assumption that just passing through all the environmental noise is totally fine because, the client's GIS team will just sort it out eventually.
And that assumption is a massive abdication of professional responsibility because cleanup in a point cloud is not cosmetic, it is structural triage.
What do you mean by structural triage?
Well, when a LiDAR sensor operates, it captures literally everything. It doesn't discriminate. It captures birds flying through the scene. It captures atmospheric dust.
Wait, it can capture dust?
Oh, yeah. Heavy dust, rain, snow. It also captures multipath reflections, like the laser bouncing off reflective glass windows and creating phantom points floating inside the interior of a building.
That sounds like a mess.
It is a mess. And if an operator leaves all that geometric noise in the final deliverable, they are forcing the end user to play detective. The end user has to figure out what is real geometry and what is just a sensor artifact.
And they weren't on site, so how would they know?
Exactly. Professional guidance dictates that the delivered geometry has to be rigorously controlled. You cannot expect a downstream engineer to know that a cluster of points 20 feet above the highway was a passing semi-truck and not a newly installed overhead gantry.
Wow. Yeah, that's a huge liability. Which leads directly into the third killer, ignoring classification. Because for anyone who hasn't worked deeply with this data, unclassified point cloud data is basically just a chaotic soup of spatial coordinates, right?
That's exactly what it is. A structural soup. Classification is the process of actually applying an identity to a point.
So giving it a name.
Giving it a category, yeah. It's the operator going in, usually using a mix of automated algorithms and painstaking manual review to say, okay, these specific points represent bare earth. These points represent high vegetation. These points are man-made structures.
Because without that classification, the data set is computationally dumb.
Exactly. It doesn't know what it is.
Like if I'm a civil engineer and I want my software to generate a topographic map of the ground, my software actually needs to know which points to ignore. If the data is unclassified, the software is just going to try to build a topographic map right over the tops of the trees and over the roofs of the cars.
Precisely. You'll get a terrain model that looks like a lumpy blanket covering a city. If you deliver unclassified data, you are silently screaming to the client, hey, you do the heavy lifting. And if that client doesn't have an in-house photogrammetrist, the data just becomes an incredibly expensive digital paperweight.
The fourth killer is actually fascinating to me because it's not a technical error, it's a psychological one. It's ego-driven assumptions.
Oh, the curse of knowledge.
Yes. The operator spends 3 days walking the physical site. They set out all the ground control points. They watch the drone fly every grid line. They know the site intimately.
They've lived there for days.
Right. So when they get back to the office and process the data, they completely forget that the project manager, who is sitting in a high-rise office 3 states away, is looking at this data set completely cold.
They don't have the context.
None at all. So the operator knows that the weird, massive gap in the data along the fence line is just because a giant delivery truck was parked there during the flight.
But the remote client just opens the file, sees a massive hole in their model, and immediately assumes the sensor failed or the processing was botched.
Exactly. They panic.
A professional bridges that contextual gap.
Mhm.
They don't rely on the client to guess. They provide heavily annotated screenshots, they clip out localized subsets of the data to highlight areas of interest, and they explicitly document every single anomaly.
They tell the story of the data.
They steward the data, yes.
And finally, killer number 5, the tourist review. And I think anyone who has ever opened a 3D model is guilty of this at some point.
Oh, everyone does it the first time.
You load the file, you grab your mouse, you zoom way in on the coolest looking building, you orbit around it a couple of times, and you say, wow, that looks amazing. Job done, send the invoice.
Sightseeing. It is the absolute antithesis of quality assurance. You are just admiring the aesthetic output of the software.
Right.
But professional review is this highly structured, almost adversarial process. You are not there to admire the cloud. You are there to break it.
To break it.
Yes. You have to assume the data contains hidden flaws, and your job is to systematically hunt them down before the client finds them.
Which is actually the perfect transition into how we do that hunting. Because you can't just fly through the data like you're playing a flight simulator.
No.
There is an actual rigorous methodology here.
Yeah.
How does an expert interrogate the evidence?
It requires abandoning that tourist mindset entirely and adopting 5 specific, deliberate navigational tools. Navigation in a point cloud is fundamentally about moving through the dataset in ways that force the underlying truth to reveal itself.
Let's break these down because honestly, understanding this completely changed how I interact with spatial data. First up, there's the pan.
Right. So panning is simply translating your view sideways, forward, backward, or vertically without altering your viewing angle.
So you're not twisting the camera.
Exactly. You keep the camera locked in its orientation and you just slide the scene past you. This is specifically used to verify linear continuity.
Like for a pipeline or something.
Exactly. If you're inspecting a massive 30-mile transmission line corridor, you set your angle so you can view the wires clearly against the sky, and you simply pan for miles. You are just watching for breaks in the wire geometry or sudden drops in point density. If you were to shift your angle while doing that, you'd introduce perspective distortion. So you lock it and you pan.
Okay, that makes sense. The second tool is the orbit.
Orbiting is when you anchor your pivot point on a specific feature. Let's say a structural column on a bridge, and you rotate the camera entirely around it.
Like 360 degrees.
Yes. This is how you test geometric stability. Because of occlusion and sensor limitations, a column that looks perfectly cylindrical from the north side might have a massive data void on its southern face.
The shadow we talked about.
Right. Or worse, if the flight lines were misaligned during processing, orbiting might reveal that the single column is actually split into 2 distinct offset sets of points.
That's like a double vision effect.
Exactly. You wouldn't see that if you didn't orbit.
And then there's the zoom. Now, everyone knows how to use a scroll wheel on a mouse. But the professional philosophy here is entirely different. You don't just zoom in and out to get a closer look at something shiny.
No, zooming should only be executed to answer a specific diagnostic question.
What do you mean by that?
Well, if you are looking at a roof edge from a wide angle, your brain interpolates a nice, sharp corner. You only zoom in to ask the data a question. Are you actually a sharp edge? Or are you a fuzzy cluster of points spanning a 3-foot margin of error?
Oh, I see.
If you zoom in without a question like that in mind, you are just sightseeing.
You're being a tourist again.
Exactly.
Tool number 4 is the slice. And this involves using bounding boxes or clipping planes to physically hide the vast majority of the point cloud.
And slicing is arguably the most powerful analytical move you can make. When you look at an entire construction site at once, the visual noise is completely overwhelming.
Too many beads in the stadium.
Way too many beats. If you want to know if a freshly poured concrete slab is truly flat, you cannot tell by looking at the whole site. So you draw a highly restrictive clipping box around just that one slab, and you shrink the z-axis bound so you are literally only looking at a slice of data 1 foot thick.
You isolate the critical volume.
Yes. Suddenly, all the chaotic cloud is gone, and you are staring strictly at the behavioral truth of that one concrete surface.
Which brings us to the 5th tool, and this is where the actual sequence comes into play, changing perspective. Because professionals don't just use these movements randomly, right? They follow a rigorous sequence of viewing angles to cross-examine the scene.
It is a highly repeatable protocol. It's designed to catch escalating levels of error. So you always start wide.
A wide shot.
Right. That is your baseline sanity check.
Yeah.
Did the dataset export in the correct coordinate system, or is it currently floating in the middle of the Atlantic Ocean because someone typed in EPSG code wrong?
Which happens.
It happens all the time. Next, you move to the top-down or orthographic view.
And top-down isn't really about looking at the buildings or the site, right? It's about looking at the flight patterns.
Exactly. From straight above, you aren't looking at the subject matter. You are looking at the coverage discipline of the sensor.
Okay, what does that look like?
Are there stark, obvious gaps between the drone's flight lines? Is the point density heavily striped? Because if it's striped, that means the overlap between photos or laser pulses was insufficient. Top-down exposes the mechanical execution of the flight itself.
Got it.
Only after you verify that do you move to the oblique angle, which is your standard 45-degree angled view. This is your reality check for structural coherence. Does the scene actually represent the physical world in a recognizable way?
But, and here's where it gets really interesting. The real magic happens in step 4, the profile view.
Oh, yes.
If anyone wants to understand why processing this data takes so much skill, it all comes down to the profile view.
Right.
Because this is the ultimate lie detector for spatial data.
It truly is. The profile view is when you drop your virtual camera all the way down to ground level and you look at the data set purely horizontally.
Like a cross-section.
Yes. It entirely strips away the visual camouflage of the overhead perspective. Let's say you have a flat warehouse roof. From top down, it looks pristine. From oblique, it looks perfectly solid. But when you slice a cross-section of that roof and view it in profile, the data is forced to confess its flaws.
What kind of flaws usually pop up here? Because I imagine this is where vertical error like z-axis drift becomes glaringly obvious.
Exactly. Vertical errors are the hardest to spot from above, and they are the most catastrophic for downstream engineering. In profile, that perfect warehouse roof might suddenly reveal itself to be double surfaces.
Meaning what?
Meaning you literally see two distinct lines of points hovering 18 inches apart from each other.
Like two roofs stacked on top of each other.
Exactly. That happens when two different drone flights overlap, but their onboard GPS calculations disagreed slightly on their absolute altitude. If you don't catch that double surface in profile and an engineer tries to calculate a structural load based on that roof, which of the two surfaces does their software choose?
It's a coin toss.
It's a complete guess.
That's terrifying. I was also thinking about how the profile view exposes wire fuzz. Like if you fly a drone over a high voltage power line and you don't have enough overlap, or the wind was blowing the line around during the flight, the profile view doesn't show a nice, tight, solid wire, right?
No, it shows what looks like a fuzzy caterpillar, 3 feet thick, just hovering in the air.
And if you are doing a clearance analysis to see if a massive oversized transport truck can safely drive under those lines, where exactly is the bottom of the wire? Is it the top of the fuzz, the bottom of the fuzz, or the dense core in the middle?
The profile view forces you to confront that ambiguity instead of just blissfully ignoring it.
This sequence-wide, top-down, oblique, profile, slice, it's brilliant because it violently shifts you from being a passive consumer of a cool 3D image into an active interrogator of evidence. You are aggressively hunting for the data's breaking point.
You have to. And once you know how to navigate to find those breaking points, you have to know how to change the visual layer to make those breaking points incredibly obvious.
Right, the display modes.
Because navigating changes how you move through the data, but changing the display mode alters the fundamental question you are asking the data to answer.
Let's talk about those modes. If you just open a standard point cloud viewer, the default display mode is almost always RGB, or true color. It essentially takes the photographic pixels from the drone's camera and drapes that color over the individual laser points.
Which is incredibly intuitive for human orientation. It makes the digital world look exactly like the physical world we're used to.
Sure.
But as an analytical tool, RGB is highly deceptive.
Because it acts as camouflage.
Exactly. Human vision is so heavily attuned to color. A beautifully colored point cloud can mask horrible structural alignment. If a building edge is smeared across a 2-foot error margin, but the points are all perfectly colored to match the red brick facade and the green grass below it, your brain will just smooth over the structural error.
Because the colors match what you expect to see.
Right, so to break that camouflage, you have to strip the color away entirely and apply different analytical filters. The first major one is elevation coloring.
So instead of coloring points by their photographic reality, you color them by their literal height above sea level.
Exactly. Elevation coloring exposes the vertical logic of the scene. Imagine you're looking at a massive parking lot in RGB. It just looks like flat, gray asphalt.
Boring.
Boring. But if you switch to a really tight elevation color ramp, where the lowest points are deep blue and the highest points are bright red, suddenly subtle grading issues just explode into view. You can instantly see the microslopes that were designed for water drainage.
Oh, wow. It also seems like the fastest way to find absolute garbage data floating up in the sky. Like if you color a site by elevation, and suddenly there's a bright red cluster of points 200 feet above the highest building.
You instantly know you captured a crane from a neighboring construction site, or a flock of birds, or just severe atmospheric noise.
Oh.
It takes 1 second to spot what might have taken hours to find in true color.
That's incredibly efficient.
High-end GIS software leverages this heavily. You can set elevation range filters to visually isolate only the points that exist between, say, 50 and 60 feet above the ground, which instantly highlights the specific floor of a building you are trying to analyze.
Okay, the next display mode is where things get really technical. Intensity. And we need to clarify this deeply because I feel like this is where so many people get confused. Intensity is a measure of how strongly the laser pulse bounced back to the sensor. But it is very specifically not photographic brightness.
Thank you. Yes. This is a trap that even intermediate operators fall into all the time. They switch their viewer to the intensity view, the screen turns into this grayscale image, and they just instinctively treat it like a black and white photograph.
But it's not.
It is absolutely not. Intensity is representing signal behavior. It's representing physical reflectivity and surface physics.
Right, because if you fly LiDAR over a freshly paved asphalt road that has crisp white painted lines on it, to our eyes, or to a camera, the white paint and the black asphalt reflect light very differently.
Yes.
But to an infrared LiDAR pulse, those materials might absorb and scatter the beam in ways that have absolutely nothing to do with their visible color.
Exactly. Or consider water. Visually, a puddle reflects light beautifully. It looks bright. But to a near-infrared LiDAR pulse, water is often just a black hole. It absorbs the beam or it scatters it away in a different direction, resulting in near zero intensity, or literally a complete void of points.
So if you treat intensity like a photo, a puddle looks like a bottomless pit in your data.
Right. But if you understand it as signal strength, it becomes this incredibly powerful tool for material classification. You can easily distinguish between a dirt path and a paved path based purely on how they return the laser, even if they look completely identical in the shadows of a true color image.
That is so cool. And that leads directly to the final display mode, which is classification. This is where you color the points strictly by the category they've been assigned. Ground is orange, vegetation's green, buildings are red, that sort of thing.
This mode instantly reduces the visual chaos of the environment. If you want to verify that an automated ground-finding algorithm actually did its job, you switch to the classification view and you just look for anomalies.
Wait, what?
Well, if you see a big cluster of orange ground points hovering halfway up a pine tree, you instantly know the algorithm failed and you need to go in and do some manual intervention.
But let me play the role of the busy project manager again.
Sure, go for it.
If I am paying a premium for this data, and all I really want to do is see the visual context of my site so I can plan logistics,
Yeah.
isn't looking at laser intensity or elevation gradients just making things needlessly complicated? Why can't I just live in the true color view?
You absolutely can as the end user. But these display modes aren't really for the client's final presentation. They are the rigorous diagnostic tools required for the operator's quality control before the client ever sees the file.
Oh, got it.
An operator cannot verify the structural truth of a scene relying on RGB alone. If a roof edge sags due to a processing error, true color might hide that sag in a dark shadow. Elevation coloring exposes it instantly. You change the question you are asking the data by changing the visual layer.
So we have navigated through the cloud like investigators. We've switched display modes to expose all the hidden noise, the artifacts, and the classification errors. The flaws are now basically glowing on the screen.
They are unavoidable at this point.
Which brings us to the actual intervention. Honest cleanup versus vanity. The profound discipline of deletion. Because once you see all these flaws, how do you clean the cloud without accidentally rewriting the reality of the scene?
And this is exactly where data processing becomes an ethical and engineering tightrope. There is a massive, massive difference between clarification and falsification.
What's the line there?
Good cleanup is about clarifying the signal. It means aggressively deleting the obvious outliers, the birds, the dust, the atmospheric noise. It means cropping away the off-scene junk at the very edges of the flight path that has degraded accuracy anyway.
So that's the good stuff. But bad cleanup. Bad cleanup is deleting inconvenient reality.
Yes.
Like if there is a light pole on the site that is leaning at a dangerous 15-degree angle, and the operator looks at it and thinks, wow, that looks messy, I'm just going to delete those points or run a smoothing algorithm to make it look perfectly straight and plumb. They aren't cleaning the data at that point. They are doing a terrible, potentially dangerous job.
They are essentially laundering the spatial evidence.
Laundering.
Yes, it's like a crime scene investigator sweeping a bloody footprint under the rug just because it makes the room look tidier for the photographs. You are actively destroying critical evidence. The strict philosophy here is that delivered point cloud geometry must remain fiercely faithful to the raw data used to generate the outputs.
Because if you carelessly alter or smooth the physical structure of the cloud, you invalidate all the downstream engineering products.
Exactly. If an engineer designs a retaining wall based on your smoothed out, heavily modified data, and the actual terrain is jagged and unstable, the wall fails. It's that simple.
And part of this honest handling of evidence is the categorization we discussed, classification. It's not just some automated magic trick. It requires intense human interpretation. And the most critical separation, from what I understand, is isolating what they call the money class.
The ground, bare earth.
The money class.
Yeah, because that is what 90% of civil engineering clients actually care about. They want the bare earth. But to get the ground, you have to successfully classify and isolate all the vegetation. And vegetation isn't just one monolithic thing. It is usually broken down into low, medium, and high classes, alongside structures and vehicles.
I was looking at how these classifications directly impact the final deliverables, and it really comes down to a crucial distinction that operators use a very catchy mnemonic to remember. The difference between a DEM and a DSM.
Yes, a DEM is a digital elevation model. A DSM is a digital surface model, and the rule of thumb in the field is always DEM digs down, DSM stays up.
DEM digs down, DSM stays up. Let's unpack that. DEM digs down, meaning it represents the bare earth terrain, essentially digging down past all the obstacles to find the dirt.
Correct.
DSM stays up, meaning it includes the top surfaces of absolutely everything, the tree canopy, the building roofs, the power lines.
Exactly. And this is exactly where classification errors become completely catastrophic. A DEM is generated by telling the software to ignore all points classified as vegetation or structures and build a surface only out of the points classified as ground.
Okay, so imagine a highway overpass spanning a deep valley.
Okay.
If the operator lazily misclassifies the concrete bridge deck as ground, the DEM algorithm will just incorporate it, right?
Yes, it will.
So instead of a deep valley with a bridge over it, the bare earth model will show a massive sheer cliff face of solid dirt blocking the entire valley.
Exactly. And if a hydrologist then uses that DEM to model floodwaters, the software will show the water damming up against a dirt wall that doesn't actually exist in reality.
That is wild. The downstream effects of poor classification are massive, which is why professional operators rely on these systematic mental checklists before they ever consider exporting the data. I want to walk through these because they perfectly encapsulate the discipline we are talking about.
They do.
There's the pre-export point checklist and the pre-delivery cloud checklist. Let's look at point first.
So the point checklist happens while you are still deep in the processing software. P stands for position right. Have you verified the absolute accuracy against your ground control points? O is for overlap reviewed. Have you actually checked the profile view to ensure your flight lines aren't creating those double surfaces we talked about? I is for intensity understood. Have you checked that the intensity values are scaled correctly and haven't been corrupted during processing? N is for noise removed. Have you manually stripped out the multipath artifacts and the floating debris? And T is for tile and type delivered. Have you broken this massive data set down into manageable geographic tiles so it won't crash the client's computer?
That is so thorough. And then once you export it, you run the cloud checklist before you actually send the email to the client.
Right. So C is coordinates checked. is the spatial reference system explicitly stated in the metadata. L is labels or classes reviewed. Did your automated vegetation algorithm accidentally grab the roof of a low building and classify it as a tree?
Which happens.
All the time.
No.
O is outliers removed. Did a weird spike in the surface model slip through the cracks? U is user format confirmed. Did you export the right file type for their specific software? And D is deliverable documented. Have you written the report explaining all the decisions, the anomalies, and the margins of error?
If an operator meticulously hits every single one of those items, they are practicing the discipline of deletion perfectly. They have officially transitioned from just being a drone pilot to being a true spatial data steward.
Absolutely.
Which brings us to the actual moment of truth. You have interrogated the data, you have displayed it to find the flaws, and you have cleaned it with fierce honesty. And you had to hand it across the table. But the reality of this industry is that one size absolutely does not fit all. You have to translate this data for the specific audience receiving it.
Translation is the perfect word, because the raw deliverables in this space are essentially an alphabet soup of file formats. If you just guess what they want, you will inevitably send a format that crashes your client's entire workflow.
Let's decode that alphabet soup a little bit. The heavy hitter in the room is obviously LAS and LAZ.
Yeah, LAS is the foundational native language of LiDAR. It is a highly structured, open binary format maintained by the American Society for Photogrammetry and Remote Sensing.
It holds everything.
Everything. It contains the spatial coordinates, the intensity, the classification, the GPS timestamps, all of it. LAZ with a Z is simply the exact same data, but subjected to lossless compression.
So LAS is loaded, LAZ is lighter.
Exactly. That's the memory. LAS is loaded, LAZ is lighter. If you are delivering classified point cloud data to a federal agency or a heavy civil engineering firm, LAZ is the undisputed industry standard. It preserves total structural integrity while minimizing file size.
But then you have E57. Why would someone request that over a standard LAZ file?
Well, E57 is an open vendor-neutral format specifically designed for 3D imaging data. While LAS was really born from airborne LiDAR, E57 is deeply rooted in terrestrial laser scanning like tripod scanners and reality capture.
So it's more for ground-level stuff.
Partially, but its real superpower is interoperability. It can store not just the point coordinates, but the actual spherical imagery taken from a tripod scanner, multiple scan setups, and really complex metadata. If your client is merging drone data with ground-based laser scans, they will almost certainly want an E57 file to bring into their registration software.
Got it. And then there is the Autodesk ecosystem, the RCP and RCS files.
Right. Because if you are handing data to an architect who spends their entire life inside Revit or AutoCAD, they do not want a raw LAS file. The Autodesk environment uses its own proprietary indexing format.
So how do RCP and RCS work together?
An RCP is the overall project file. Think of it as the binder. The RCS files are the individual index scan regions, the pages inside the binder. If you deliver a pre-indexed RCP and RCS package, the architect can just drag and drop it into Revit instantly without spending 6 hours watching their computer struggle to index the raw points.
You're saving them so much time. But not every stakeholder is an engineer or an architect. Sometimes the client just needs derived outputs. They don't want the massive cloud at all. They want 2D contour lines or the Bareth DEM we talked about, or even just a lightweight web scene they could view in a web browser.
And this is exactly why an operator must be a translator. You cannot hand a C-suite executive a 50 gigabyte LAZ file.
They'll hate you.
They won't even be able to open it. They don't have the software installed, they don't have the processing power on their laptop, and they frankly don't have the time. An executive needs a lightweight 3D web link, annotated screenshots highlighting the areas of concern, and a one-page summary of the volume metrics.
Right.
Conversely, a field construction crew doesn't need the whole 50-acre site. They need a heavily clipped, super lightweight view of just the excavation pit so they can plan where to safely park their heavy machinery tomorrow morning. But the lead engineer, they absolutely need the dense, classified LAZ file to run their own structural analyses.
So, practically speaking, how does a true professional handle that incoming request? Because when a client calls and says, hey, we need you to fly the site, just send me the point cloud when you're done. How do you intercept that without sounding condescending?
A professional operator never just says, sure thing, and attaches a random file. They immediately answer with a diagnostic sequence of questions.
Like what?
What specific software environment are you using to open this? Do you require the data to be pre-classified into ground and non-ground? Are you looking to extract raw measurements from the spatial data yourself? Or do you actually just want me to generate a clean terrain model and send you the CAD surface?
You are saving them from their own lack of expertise. You save the client from having to know how to ask for the right thing perfectly.
Exactly. You guide them to the specific deliverable that solves their problem without inducing friction.
But here's the critical pivot. We have spent this entire deep dive treating the technical quality of the data as gospel. We have talked about how to make it perfectly accurate, perfectly clean, perfectly classified. But an analytically brilliant, mathematically perfect point cloud is fundamentally worthless and actually represents a massive legal liability if the operator broke the rules of the sky to collect it.
Oh, absolutely. The regulatory wrapper.
This is where technical capability slams face first into legal reality. Because a point cloud is essentially a legal document representing the state of the world at a specific moment in time. If you acquire that document illegally, it is completely compromised.
It's entirely compromised. We have to look at the compliance environment, specifically in North America, because the rules dictate the defensibility of the final product.
Let's start with the Canadian framework. How are remotely piloted aircraft systems, or RPAS, regulated up there when it comes to capturing this kind of high-end data?
So, under Transport Canada's CARS Part 9X regulations, the landscape has historically been divided into basic and advanced operations, which is largely dictated by your proximity to bystanders and whether you're in controlled airspace. But the critical evolution taking place right now, moving into 2025 and beyond, is the formalization of Level 1 complex operations and the introduction of RPAS operator certificates, or RPOCs.
Why is that a game changer for spatial data collection specifically?
Because it opens up highly structured, lower risk pathways for beyond visual line of sight, or BVLOS, flight.
Oh, wow.
Yeah, if you are trying to map a 40-mile transmission line corridor to create a point cloud, doing that by keeping the drone within your physical line of sight the entire time is agonizingly slow and wildly inefficient. The RPOC framework allows highly professional outfits to push further legally, meaning they can acquire massive corridor datasets seamlessly.
And what about south of the border? The United States airspace under the FAA.
In the U.S., the foundational framework for commercial small UAS operations is 14 CFR Part 107. That is the bedrock. But the real complexity comes with the operational requirements built on top of it, specifically remote ID.
Right, which became a hard operational requirement in September 2023.
Yes. Remote ID is essentially a digital license plate broadcasting the drone's position and the pilot's location in real time. And beyond that, if your mapping mission requires you to fly over active traffic, or maybe you need to fly at night to avoid thermal shadows from the sun, you can't just do it. You have to navigate the complex waiver logic of the FAA to prove exactly how you will mitigate the risk.
What I find so striking about the regulatory environment is that the aviation authorities do not care how beautiful your point cloud is.
They do not care at all.
There is no special LiDAR pilot certificate that lets you bypass the safety rules just because you are doing complex, expensive engineering work. The regulations attach purely to the physical aircraft and the kinetic risk of the operation.
And that is the core tenet of defensibility. Imagine a scenario where a civil engineering firm is sued because a newly constructed retaining wall collapsed. They pull up the point cloud data in court to prove that their volumetric calculations were based on accurate terrain models.
Okay.
If the opposing counsel discovers that the operator who collected that data flew an unregistered drone over an active highway without a Part 107 waiver to get those specific angles, that data instantly becomes a massive liability. A great mapping mission flown outside of operational limits produces a fragile, legally indefensible product.
Technical perfection cannot cure operational illegality.
Perfectly stated.
So defensibility means pairing operational honesty with data repeatability. Let's take everything we've discussed today, the capture, the navigation, the classification, the formatting, and the legal constraints, and see how this all manifests in specific real-world environments. Because what constitutes perfect spatial truth shifts dramatically depending on the industry you are serving.
It does. The mission objective entirely dictates what data matters and what data is considered noise. Let's analyze 4 distinct operational environments to show how different they are. First up, utility corridors. Think rail lines, pipelines, and massive power transmission routes.
Why is this considered one of the most unforgiving environments for data processing?
Aggressively, because corridor work aggressively punishes lazy review. From a wide, zoomed-out angle, a 50-mile corridor point cloud always looks incredibly impressive to a layman. But the utility client isn't paying for the wide shot. Their entire risk profile lives in the micro details.
Like what?
The focus here is on linear continuity. You are hunting for wire fuzz to ensure the power lines aren't sagging beyond safety margins. Most importantly, you are obsessing over ground visibility underneath incredibly dense tree canopies. If your LiDAR sensor didn't punch through the leaves enough to establish a solid ground model, you cannot accurately measure the distance between a drooping power line and the earth below.
And if you get that wrong,
If you fail to classify the encroaching vegetation correctly, the utility company might miss a critical trimming cycle and trigger a massive forest fire.
the stakes are literally astronomical. Okay, now contrast that hyper-detailed requirement with something completely different, stockpiles, like mining and aggregate sites.
With stockpiles, the rules change entirely. The client does not care about the cinematic quality of the scene. They don't care if the texture of the gravel looks realistic. They care about exactly one metric: volume confidence.
How much dirt is in the pile?
How many cubic yards of material are sitting on that dirt pad? The operator's focus shifts entirely to aggressive isolation. You have to meticulously delete the front-end loaders, the parked dump trucks, and the temporary conveyor belts. Then you have to find the definitive toe of the pile.
The toad.
The exact perimeter where the gravel pile meets the natural, flat ground. If you misidentify the toe by just 6 inches around a massive, sprawling pile, you introduce thousands and thousands of dollars of error into their inventory calculation.
Okay, what about urban architecture? Buildings and facades.
Here, geometry is king. A stockpile requires you to capture a lumpy mound of dirt, but facade work rewards absolute geometric crispness and brutally punishes smeared edges. If an architect is designing a complex glass curtain wall to retrofit onto a historic brick building, they need to know the exact plumb line of the existing structural corners.
Down to the millimeter.
Yes. The focus is on capturing sharp overhangs, deep window recesses, and completely avoiding any alignment artifacts where 2 flight passes might double up the wall thickness. And crucially, this is where your format translation matters most, because the deliverable almost always has to be seamlessly integrated into Autodesk Revit as an E57 or RCP file.
And finally, the environment that just sounds like an absolute nightmare to fly and process. Electrical substations.
No, substations are the ultimate crucible for an operator. They are high-consequence, kinetically dangerous environments. You are physically flying around high-voltage infrastructure. But from a data perspective, they are a nightmare because they are incredibly dense and full of complex metallic structures.
Which messes with the laser.
Terribly. Metal grating, chain link senses, and reflective insulators scatter laser pulses wildly, creating massive amounts of multipath noise. The entire goal of processing a substation point cloud is congestion clarity. You have to aggressively slice and filter the data to separate temporary site clutter like a parked maintenance truck or a discarded ladder from the permanent, highly dangerous electrified hazards.
It is wild to me that if you took a perfect point cloud of a stockpile where you have aggressively clipped away absolutely everything except the dirt to give them exactly what they want, and you handed that style of hyper-minimalist data to an architect designing a facade, they would fire you immediately for delivering an incomplete, contextless mess.
They absolutely would. The mission objective completely dictates the definition of the payload.
Which loops us perfectly back to the core philosophy we established at the very beginning of this deep dive. The actual product a spatial data professional is selling is not a 50 gigabyte file containing billions of 3D dots. They are selling reduced uncertainty.
They are selling the ability for a lead engineer to sleep at night knowing the clearance measurement they signed off on is mathematically real.
Exactly. So for you, the listener, the ultimate mental model to carry forward when interacting with 3D spatial data is this. You must navigate to understand. You must change your display modes to reveal the hidden flaws. You must clean the data aggressively to clarify the signal. And you must classify the points to focus the algorithm.
A point cloud isn't finished the moment the drone lands, and it isn't finished when the file successfully opens on your workstation. It is only finished when the right stakeholder can look at it, inherently trust it, and safely act on it. Data delivery is simply saying, here is every measurement my sensor took, good luck. Value delivery is saying, here is the exact structural evidence that matters, here is why it matters, here is the specific file format your software requires, and here is the exact margin of error we are confident in.
And that leads me to a final thought I want to leave you with. Something we haven't touched on today, but feels like an incredibly urgent question as this entire industry evolves. We are currently watching software tools roll out advanced AI algorithms designed to automatically ingest these raw point clouds, automatically classify the ground, automatically delete the noise, and generate a perfectly smooth, photorealistic 3D mesh with zero human intervention.
It looks like pure magic.
It does. It looks like magic. But what happens to all that rigorous human skepticism we've spent the last hour talking about? If operators start blindly trusting the AI because the first pass mesh looks flawlessly beautiful on a monitor, are we actually eliminating the errors, or are we just burying them deeper? Are we setting the engineering world up for a massive wave of catastrophic structural misinterpretations, all hidden beneath a beautiful, artificially generated, completely uninterrogated illusion?
That is a terrifying but very real possibility.
It is something to seriously ponder the next time you zoom in on a flawless 3D digital twin of the real world. Just remember that massive file strain in your graphics card. Are you looking at structural reality, or are you just staring at a billion glowing beads in a dark stadium, letting your brain fill in the blanks? Thanks for joining us on this deep dive.
That's a wrap on today's mission, Commander. See above, go beyond, get ahead. For more training, tools, and intel, head to skycommander.ca. If you learned something new, share it, subscribe, and leave us a 5-star debrief.